The objective of my lectures is very modest, simply to try to gain some confidence with the classical energy criterion, which engineers use all the time to assess the stability of structures in the conservative case, right? So when I say the conservative case, I mean also possibly in the presence of dissipation. So why should we believe the energy criterion? It's easy, quote unquote easy, to establish in the finite dimensional case because we have various mathematical conveniences like compactness of the epsilon ball in finite dimensions and so on, and differentiability implies continuity, things like that. They're easy to enforce, and we've seen it's not so easy in the continuous system. Something like a rod, which is my sort of prototypical example here, is the easiest continuous system to study, where we can do something. We can establish continuity via Frechet differentiability. We can establish, what else? Under the assumption that our energy, the energy difference away from equilibrium, is bounded below by some strictly increasing function. We can verify the hypotheses of the usual Lagrange-Dirichlet or Lyapunov theorem, and then obtain sufficient conditions for stability. Simple positivity of the energy was enough in the finite dimensional case because of the compactness of this epsilon sphere in finite dimensions and the continuity of the energy. And that was crucial in making the theorem work in finite dimensions. That's not the case here in the infinite dimensions because this epsilon sphere is not compact in a function space. And so we need to bound the energy from below by a strictly increasing function. So the problem then is you have an actual structure and you don't know a priori if these things are satisfied. And we show, at least for conventional structural systems exemplified by rods, that in fact you can carry out this program. So let's just continue that program. We're going to try to verify this inequality. F2 is the second variation at some perturbed state. So V stands for the transverse deflection. Remember the master degree of freedom, if you like. And V is any value of that transverse deflection. And we'll use the energy norm for reasons we indicated last time. So we would like to show this inequality, which then guarantees that the second variation, remember the second variation we established is also the second second Frechet derivative. And this bound would then guarantee that the energy itself is bounded below in a sufficiently small neighborhood of the origin as measured by the energy norm. Okay? So we would like to show that there is, to establish this inequality with lambda some strictly positive constant, then this has the interpretation of the infimum of this ratio. Right? And if we are successful in finding a range of forces, applied force, remember F is this is bad notation, F is the applied force, and F2 is the second variation of the second Frechet derivative of the actual energy function. So we would like to establish a range of forces, applied forces, for which we can verify this inequality, and then we're guaranteed stability by the theorem that we proved last time. Okay. Our strategy will be, let's pick a positive lambda and then find a V naught that satisfies this ratio, for which this infimum is actually achieved. Okay? So one can actually a priori prove the existence of such a V naught. There are some references here. But our strategy will just simply be pick a V naught and then find V naught to satisfy this inequality. Okay? So we'll prescribe lambda and then find the V naught that makes this into an equality, and then show that we can verify this inequality for all other v. So suppose there is such a v naught, and write v as the perturbation of v naught by some epsilon. F2 is the second Frechet derivative at v naught. It's a quadratic functional, and we found it last time. It's this, right? In the presence of an applied force, compressive force. So the physical system is we have a rod clamped at one end at the left and clamped into a block at the other end, and the block is free to slide horizontally, and that's the only allowable motion at the right-hand end. So this is then an exact expansion. It's a quadratic functional, so it terminates at order epsilon squared. This is F2 at v naught, this is F2 at the perturbation W, and the W must be such that V is kinematically possible, so it meets the kinematic conditions of the problem, boundary conditions. And the linear term then will just be the Gateau derivative of F2 at V naught in the direction of W. And we've computed that before. It's simply this. Okay. And let's suppose this is true now. So if V naught is the minimizer, such that this ratio is equal to lambda when epsilon is 0, then we can attempt to find V naught to make that a minimum. So here this is the squared energy norm of this perturbation, and simply by expansion we compute it to be this. The square bracket is the Micklin energy product, inner product, and the induced norm is just the usual energy norm then, induced by that inner product. So the assumption is, as a function of epsilon, this combination is positive, is never negative, and is equal to 0 when epsilon is equal to 0. And this, of course, then is a quadratic function of epsilon, and under these conditions its derivative has to vanish at epsilon equals 0. That just gives us this problem, which is a linear variational problem. Okay? And at least in our system, that's an easy problem to solve. Notice that if we put W equal V naught in this equation, we have the Gateau differential of F2 with a half is just F2 itself with V naught, because F2 is quadratic. So we have this, and we know already that this is our second Frechet differential at V naught. Okay? So we try to solve this very easily. With the prescribed value of lambda, we choose lambda. So the critical state in the problem would be, see, df2 would be 0. That would correspond to the buckling condition. So let's rewrite this linear variational problem in this way, and we have the lambda that we're choosing here in this term. Okay? We choose lambda, strictly positive, and then we verify the hypotheses of the theorem. So the test function W must meet the geometric requirements of the problem. In our case, it's clamped at the end and clamped at the other end into a cement block that's free to slide back and forth. And then we can simply do some integration by parts, invoking those boundary conditions. And that linear variational problem reduces to this, so you immediately see we're going to extract an Euler equation for that problem, which is this. If lambda is 0, this would be the equation of linearized adjacent equilibrium, and the solution V naught would be the buckling mode. Right? So we'll just solve this for some positive lambda. The character of the problem depends on the sign of this coefficient here. So lambda has the effect of adjusting the flexural stiffness. Let's pick this parenthesis so that this effective flexural stiffness is positive. We simply need lambda to be positive. And that condition then can then be met by taking lambda, but strictly between 0, or including 0 up to, but not including 1/2. Okay? So let's choose lambda between 0 and 1/2. If we can fulfill the program for lambda in this range, then we have the hypotheses of the Lagrange-Dirichlet satisfied. So this Euler equation then reduces to this, or a standard eigenvalue problem. And under our assumptions, the coefficient is positive then for lambda strictly less than a half. And we solve it easily and impose our boundary conditions, and then we have the usual problem in buckling, except with this effective stiffness, EI multiplied by 1 minus 2 lambda. So for a solution, a non-zero solution, we need this determinant to be 0 that comes from these boundary conditions, and that selects alpha. So there are two possibilities for solving this determinant. Sine alpha L over 2 is 0, or tangent, or this transcendental equation, tangent alpha L over 2 is equal to alpha L over 2. The idea is we prescribe lambda, strictly positive, less than a half, and seek the smallest force, therefore the smallest alpha, such that we have a non-zero mode V naught. And then we will attempt to prove stability for F, the force less than this value. So there are two possibilities for the roots. The first solution gives us this. The second, the transcendental equation, gives us this. This is the smallest root, so let's look at the smallest root. Okay? When lambda equals 0, this root, this is defined from the definition of alpha, is just this. And so the ratio is related to 1 minus 2 lambda. So if we're successful for lambda in this range, then alpha naught is less than alpha, which means we expect to have then stability in the range f over ei square root less than this alpha star, which is 2L. In other words, if f is less than this value, and this value is we call the critical load, that corresponds to lambda equals 0, which is just on the verge of failing the stability criterion. Lagrange-Dirichlet just begins to break down when lambda approaches 0. So this is the expectation, and now we have to prove it. So in other words, a sufficient condition for Lyapunov stability can only be fulfilled with lambda positive, which means F strictly less than this value. This is the Euler load. Okay? And at this value, Fc, we have lambda equals 0, and our Euler-Lagrange equation for the V naught reduces exactly to the standard linearized equation of adjacent equilibrium, the buckling equation. Okay? With the actual flexural stiffness there. Okay. And at lambda equals 0, which is when this equation is operative, then the second variation vanishes at that point. In other words, the second variation vanishes when the force is equal to this so-called Fc. We want to prove stability for forces less than that. And here's the mode that we get in this case. Okay? So let's select a lambda, as we indicated, and verify this inequality. See if it's true or not. So let's form the difference, and we have some terms here involving the loading term. We recognize this as the energy norm, and we have this additional term. And so we need to estimate this. We can estimate this using our previous integral inequalities from the classic book of Hardy, Littlewood, Polya, for example, under our conditions. This is like a Sobolev inequality, and it can be used to bound the size of this loading term in terms of the energy norm itself. Okay? And what I want to draw your attention to is this second derivative term here, which is associated with the energy norm. Okay? So then we have this combination then for lambda between 0 and a half is bounded below by this. You notice that for the lambda terms 1/2, 2, they drop from both sides of the equation. Let's see what's important here. Yeah, here it is again. The lambda drops from both sides of the equation, and you have this satisfied. So indeed, for f less than this so-called critical value, we achieve the second variation bounded below by the squared energy norm. And that's enough. That's enough to guarantee Lyapunov stability. So we have a rigorous stability result in the dynamical sense for such forces. Okay. And of course, if F is a tensile force, so F was defined positive when compressive, tensile force is negative then, and we have this. So in the tensile case, we always have a strictly positive second variation, in fact bounded below second variation, and we always have stability. Here we lose our sufficient condition for stability when F equals Fc, and in fact if F is greater, the compressive F is greater than Fc, we have a negative lower, we can only prove a negative lower bound, which is not enough. So if F greater than or equal to Fc, we fail to satisfy the hypotheses of the Lagrange-Dirichlet theorem. Okay, so here's an example where we can rigorously prove stability. This situation is generic in structural mechanics. In theories of plates and shells, for example, there's a bending energy, which involves a quadratic term and a curvature. This brings in second derivatives of transverse deflection, analogous to the second derivatives of transverse deflection in the beam theory, this rod theory. And if we construct an energy norm in a similar manner, we can use Sobolev F-type inequalities to prove, to fulfill all the hypotheses of the Lagrange-Dirichlet theorem. So it's that second derivative in the energy that is extremely useful in proving the theorem. And in conventional finite elasticity, for example, we have a strain energy function that typically depends on the first gradient of deformation, and that's all. There's no second gradient term. You can begin to appreciate that the procedure will break down. In fact, to this day, no one has been able to replicate this procedure, as far as I know, for standard finite elasticity, in which you have a single gradient only appearing in the energy function. For structures, we do have this generic situation that we have here. So the theory of dynamical stability is much better established for structures than it is for conventional continua. Okay? Let's see what we can say about instability. The situation here is in some sense easier. To guarantee stability, we needed this continuity of the energy with respect to the selected norm. We needed a strict lower bound, in other words, the energy bounded below by an increasing function of the norm, and those were then sufficient for stability. We can actually prove we can actually prove instability under much weaker conditions. What we can show is we can prove that if the change in energy away from an equilibrium state, if there exists another configuration with a lower energy, not equilibrated, just any geometrically possible configuration with a lower energy than the equilibrium energy, so that this epsilon we had before, which is the change in energy, if there exists a state for which that is strictly negative, that's like the indefinite case in the finite dimensional system, then we have instability. We can construct a kind of Chitaev function. So there we don't need continuity arguments, we don't need Frechet differentiability or any such thing. We simply need the change in energy. There should be a state at which the energy is strictly less than the equilibrium energy. That by itself, interestingly enough, is sufficient for instability. So we can sketch a proof of that. So for some years in the literature, especially say the 70s, I would say, around the time of this well-known treatise, Knops and Wilkes in the Handbook der Physik on elastic stability, there was a kind of industry proving instability theorems, instability results. The idea is this. So let's see if we can construct a function we could call it a Chateya function, I suppose, g of t, which is such that it bounds the squared energy norm of our transverse deflection in the rod theory from below with some positive constant. And we want to find conditions that are sufficient for this function g of t to grow without bound. Then if we're successful, we force the energy norm to grow without bound. So we'll then make an assumption that leads to a contradiction. We'll assume, you can't see it here, we'll assume stability, which means in particular the energy norm of the transverse deflection has to be bounded. And that assumption will lead to a contradiction at some particular time. There'll be a time at which that assumption will be contradicted if we're successful in carrying out this program. So we want to find conditions that yield the unbounded growth. We want to find a function g, first of all, and conditions that yield its unbounded growth on any motion of the system. So let's see. One can look back at finite dimensional systems for guidance about how to choose such a function. All we need is a function, and there was no particular systematic procedure in the finite dimensional case. Let's pick a similar function in this infinite dimensional case. Let's say this one. U is the transverse deflection. So we have this. So we intend to show the unbounded growth, we intend to integrate some some differential inequalities involving g, which will involve some derivatives of g with respect to time. When we take a derivative with respect to time, you see we'll begin to bring in some inertia terms, right? And we can use the equations of motion to rewrite those inertia terms. The useful thing about this is we can use our integral inequalities from last time to bound this term above by the energy norm of u. And likewise, this term, we can bound it above by, again, the energy norm, the squared energy norm of u. So we can claim then with this choice of g, there's a constant such that it's bounded above by a positive constant times the squared energy norm. So all we need to do now is to find some sufficient conditions to cause this g of t to grow in time. And then we're guaranteed instability. So we calculate some time derivatives. And I'll go over this quickly because it's routine. And so we have some inertia terms, and then we can use the equations of motion to balance those. So let's see, for example, we have our horizontal deflection in terms of the transverse deflection from inextensibility. We can calculate these derivatives and so on, and it's a little bit of uninteresting labor, so I won't belabor it. If you remember in a proof of Frechet differentiability, we made use of this kind of inequality, some constant m bounded above by the energy norm. We'll make use of this again, and it's not so interesting, so I'll move quickly through it. Ultimately then we can, because of the integral inequalities at our disposal, we can have a lower bound for the second time derivative of this function g we've introduced. And there's that constant m, which can be made as small as we like by controlling the energy norm of u. And here's some inertia terms. And it's not quite rigorous to do this, but let's use the linearized equation of motion for transverse deflection to say something about these terms here. And in the remainder of the notes, I repeat this discussion using the nonlinear equations to get the same conclusion, so you can read about that since you will have access to those notes if you want to. We want to connect this. Yeah.
So you use Lagrange, all the Lagrange equations deduced by your variational function.
Yeah, I'm using equations of motion, although I only use so far Euler Lagrange in the case of bifurcation of equilibrium, but yes, the same idea. So we're going to evaluate the lower bound for any motion of the system, right? But I will make I will do something not quite rigorous here for the moment by using the linearized equation of motion so that you get an idea of what I'm doing. In the notes I won't talk about here, right here, There are some notes beyond this page, these pages, where I redo the calculation using the fully nonlinear equations with the same conclusions. So this is just to give you an idea of what's going on. Okay, actually we can, if we remember the formula we had for the Gateau differential of the second variation from before, we can relate one of these terms to this second the Gateau differential of the second variation and use some boundary conditions. Okay, so we have this expression then, which is almost what we want. If w is equal to u, then this would be the expression we have here. But when w is equal to u, we have this, which is exactly twice the second variation itself, because we have u here, and this is a quadratic functional, so we have this equality. And we've established before that this is the second Frechet differential of the energy, the total energy. So then we have this right here. So you can immediately see that without doing any more analysis, that if this second Frechet differential is negative strictly, then because the kinetic energy is positive definite, we can cause this g of t, the second derivative of g of t will be strictly positive. In particular, it'll be greater than this number, if you can find a configuration that makes that strictly negative. So if we remember what the second Frechet differential is, it's this, right? So we have, at the equilibrium state, by definition, we have epsilon, the energy difference, being 0. At the equilibrium state, at 0, the first variation vanishes because we have equilibrium there. So the expansion starts at the second Frechet differential, and there's a remainder term of order energy norm, small o energy norm squared. And this is messy. I apologize for that. Ultimately, we get this inequality. M is controlled by the energy norm. We can make this as small as we like. This is the Hamiltonian, which is equal to its initial value. And if we have no initial velocity, this is simply the actual potential energy at the initial condition that we choose. Okay? So let's look at a perturbation with 0 initial velocity starting from rest but not in equilibrium state. Okay? It's just the velocity is 0 at time 0 but not subsequently. Okay? So this is our initial shape, let's say. And so this h of t is simply then, by virtue of the Hamiltonian structure of the problem, is equal to the initial potential energy as a function of the transverse deflection. Then we get this plus the remainder terms that can be made as small as we please by controlling the size of the energy norm. So let's suppose the equilibrium state under an axial load is stable. So if you recall our definition of stability, that we use this norm here to measure the size of the disturbance, where we're using the energy norm on u. So this defines the norm that we're using for the motion. Okay? So if we control the initial condition in energy norm, then we achieve this. This is the assumption of stability. That means that constant, which is controlled by the energy norm, which figures in these simple manipulations, is also bounded above by a number that depends on epsilon. And we can arrange the definition of epsilon in our definition of stability to give this kind of inequality, where this is now the second variation at the initial condition, where we use the Hamiltonian structure here to assert that the Hamiltonian at time t is equal to its initial value. And then this is a term that is small o energy norm squared, therefore small o epsilon squared. Okay? So let's say F2 at the initial condition is strictly negative. So that means minus 4 F2 is strictly above some positive constant. Okay? And we can choose epsilon small enough so that this term then dominates the inequality. And we have this simple differential inequality. And we're assuming here, we have to ensure that G double dot cannot be 0. That means we don't want our initial condition to be equilibrated, because if you look back at the definition of G, if it were equilibrated, then the velocities would be persistently 0 in an interval of time, which means G dot and G double dot and so on would be 0, and we could not have this. So the proviso is the initial condition is just a shape, it's not an equilibrated shape. We had something similar in the instability theorems for finite dimensions. Okay, so with 0 initial velocity, the G dot at 0 is 0, so we can only say this, but that's enough. We integrate this obviously again, and we can then force the norm of our disturbance to grow without bound. So there's some time at which we reach a contradiction if we make our assumption of stability. Okay. So here on this 173.1, etc., I redo the calculation using the nonlinear equations of motion and reach the same conclusion, so I won't bother you with that. I think I need to change now to another file. Okay. Yeah, so this is just a repetition of the argument with the nonlinear equations of motion so that you can follow it if you want to. There's some technical issues that need resolution, but we get the same conclusion. Let's see. Oh. So the question is, can we find such a configuration that makes the second variation, which is the same as the second Gateau, second Frechet differential, can we find a configuration to make that negative? Well, we have a configuration available to us, which is the buckling mode associated with the critical condition. Remember, we had that determinant equation equal to 0, and we found this root alpha and so on. Well, the associated mode is this. So this is the so-called buckling mode. And let's investigate the second variation on that mode. Okay? If we do so, we'll involve, if we remember what the critical load is, then we can write the second variation in terms of this constant, whatever it is, it's squared, some non-zero constant, in terms of the applied force and the critical force. Okay? So we have then a mode, we have a geometrically possible configuration, which is such as to force the second variation to be strictly negative when F exceeds the critical load. So the compressive force is above the critical load. Okay? And therefore, the straight configuration is unstable by virtue of the fact that we've now fulfilled the hypotheses of the instability theorem. So the question is, well, I said a moment ago, this initial condition cannot be an equilibrium shape. And in fact, it's not an equilibrium shape unless the force is equal to the critical force. So when the force is above the critical force, this is not an equilibrium shape. Okay? So we're fine from that point of view. Let's see. Yeah. So what we have then is a sufficient condition for instability. We could say, an indefinite second variation. That is to say, there exists a geometrically possible configuration which makes the second variation strictly negative. That implies instability. So it's sufficient for instability. So we can turn that statement around. It means that if we have stability, the second variation must be non-negative, right? So that we find that the non-negativity of the second variation at any geometrically possible configuration is a necessary condition for stability. We've already seen before that we could not convert this to a sufficient condition for stability. Okay? It's only necessary. What's interesting about this is that there's no boundedness requirement on F, there's no continuity requirement. In fact, there's not even a norm in this particular discussion here. So, okay, so...
excuse me,
yeah.
say this because you have a counterexample.
Well, right, we have constructed, by example, we found a function, this g of t, which can be made to fulfill the hypotheses of this instability result. We can make it grow under this condition, strict negativity. If we can find a configuration to make the second variation strictly negative, that's the analog of the indefinite case for finite dimensions, then we can prove this instability result. We can prove that the assumption of stability leads to a contradiction, in other words.
No, okay, I wanted to say if your second hand line,
yeah, this one?
right-hand side in the implication is true,
yeah, that's not sufficient.
then this does not imply it is stable.
No. It's only necessary because all we've been able to do is prove that this is sufficient for instability. Therefore, it's like A implies B means not B implies not A. That's all.
You have a counterexample.
No.
At this stage, logically, you cannot exclude that the B implies A. So you need to give an energy for which...
Yeah. We've only no, not really. We've only been able to prove, we convert this into a sufficient condition if we can replace the right-hand side by a positive constant times the squared energy norm. That's stronger than this. Okay, that's stronger. So this is not positive definiteness anymore, not even bounded below. So we cannot implement the program of the Lyapunov theorem, or the Lagrange-Dirichlet theorem in this context, because we needed the lower bound to be able to, if you remember the details of the Lyapunov theorem, we needed to be able to contract the initial condition such that we could get below that lower bound via the continuity conditions that we proved using Frechet differentiability and so on. So this is much weaker than that and is not enough to fulfill. This only gives us the infimum of the Hamiltonian on the epsilon sphere is 0. That's not enough. We need an infimum strictly positive to generate the hypotheses of the Lyapunov theorem. So it's only a necessary condition. But it tells you should be careful when you have equality, when this breaks down, right? So that's the status, essentially, of the subject in infinite dimensional systems. I could tell you about finite elasticity, but I think I don't really have time since I only have 15 minutes left or so. So I'll just tell you the story. In finite elasticity, we have a similar structure. We can make a Hamiltonian system. The strain energy function, typically in the standard theory, a la Cauchy and so on, depends on one gradient. It depends on the deformation gradient. Here we have previously a theory in which we essentially have a second gradient theory, right, because of the curvature dependence of the energy. So we would like to know, can we carry out the program again for finite elasticity? The program is demonstrate the Frechet differentiability of the energy function and so on, right? So this is how we implemented the Lagrange-Dirichlet theorem, to prove the Frechet differentiability. And in fact, some wrong papers were written in which it was merely claimed that for finite elasticity, the energy is Frechet differentiable. And then someone named Martini. By the way, there's a fourth file in these notes you will have access, in which you have some homework problems, if you want, and also some papers, including Martini. And he gave a proof that the only time such an energy function, so you have a strain energy function like this per unit reference volume, let's say. So in components, this would be something like this. Current coordinates, initial coordinates, and this generates the matrix of deformation gradient. Martini showed the only time you can have Frechet differentiability is when this function is quadratic. So for example, it looks like this. And then we can add a constant to make the energy 0 at any particular state, for example, when F is the identity. Right? So I'm not proving this for you here, but there's a nice brief proof in Martini. But normally we want to impose the rotation invariance of the energy. So if you replace F by QF, where Q is a uniform rotation, we don't want the value of the energy to change. That means this gets replaced by QIKFKA, and this gets replaced by QJLFLB. And we will see, because there's no saturation of indices here, even though Q is a rotation, we cannot recover the original energy. If we had QIK, QKL, or QIK, QIL, then we could use the orthogonality of Q to recover this, but we don't. So this will not be equal to this. So for physical reasons, this purely quadratic dependence on F, which is required by Martini's theorem on Frechet differentiability, is unphysical. So to this day, to my knowledge, no one has succeeded in implementing the program that we described just now for conventional continuum mechanics. Around the time of Como, Grimaldi, and so on, they were in contact with Coiter, I believe, and Coiter independently realized that if you add a second gradient, df dx, which is second derivatives of current position or displacement, then you can invoke inequalities similar to what we've had in the case of rod theory, Sobolev type inequalities. So either prove directly this lower bound that we need in implementing the Lagrange-Dirichlet theorem, or indirectly by demonstrating the Frechet differentiability of a strain energy function augmented by, say, a simple quadratic term in displacement gradient. So you have, say, ui comma j can be written entirely in terms of strain and strain gradient, it turns out, for geometric reasons. And that's enough to recover the program that we've just described in the case of beams. So if you augment conventional finite elasticity by adding a term which is in most cases undetectable in practice, an arbitrarily small positive definite strain gradient term, then you can implement the same program that we've just described, establish the Frechet differentiability, hence the continuity, the lower bound, and so on. And then you can connect energy rigorously then to Lyapunov stability with respect to an appropriate energy norm, which is based on the highest derivative terms, just as in the case of the rod theory. So it's possible to prove a sufficient condition for stability for such an augmented theory. And this is apropos these days because strain gradient theory is coming back, finding many applications. Francesco mentioned an interesting one this morning. Okay? So there it's possible to prove rigorous dynamical stability results in a problem like that. So it's possible to state a Lyapunov type theorem for conventional finite elasticity, but to actually implement, to actually verify the hypotheses of the theorem is a practical impossibility without the Frechet differentiability which we do not have in conventional finite elasticity. So as far as necessary conditions are concerned, so one can do something similar to what we did here for constructing a Chitaev function. One can virtually imitate this construction that we've just had verbatim for conventional finite elasticity, and again prove that, say, epsilon, which would be, say, the energy at some equilibrium state, or actually some kinematically possible state, minus the energy at some equilibrium state. This negative, again, can be shown to imply instability. So that if we have stability in the Lyapunov sense, then the energy at our equilibrium state must be no greater than the energy at any geometrically possible state. So again, we only have the necessity of this inequality. So for infinite dimensions, for continuous systems, the decision, the analysis is difficult because whereas this was sufficient for stability in the finite dimensional case, if you remember, because in the finite dimensional case we could use this to generate the lower bound that we needed to implement the Lyapunov theorem. This was always sufficient for instability, this was sufficient for stability, and we have essentially, apart from the critical case, we have essentially the entire problem solved in the finite dimensional case just by looking at the energy. Not so here. Conditions that are sufficient for stability, the converses of those conditions are not, they're not the same as the conditions for instability. So let me put it this way. Condition like this, which is necessary for stability, is not sufficient. That's what I mean to say. Okay? So you don't have necessary and sufficient conditions for continuous systems. You have sufficient conditions and separate necessary conditions, which are much weaker. In the finite dimensional case, that's effectively not so. Conditions that are sufficient are also effectively necessary apart from the critical case. So that's what makes the rigorous connection between energy, the energy criterion, the rigorous connection between that criterion and dynamical stability, that makes it much more difficult in the continuous case. Another way to demonstrate this, apart from the construction of a Chitaev function, is just to use thermodynamics, basically. So the general program in continuum mechanics is that the equations of motion will imply something like this, right? A power balance, K is the kinetic energy, so in any motion of the system we have this, where this is the stress power, so-called. We constructed this for the case of rods. You implement it again in continuum mechanics in general. P is the power of the applied loads. Let's suppose in the conservative case, the power is the derivative of something, call it L, ddt of L. L is the so-called load potential, the potential energy of the loads. And typically, if you have elasticity in the system, S comes from an elastic part, or a rate of change of an elastic energy, plus something else. And if you have dissipation in the system, this something else will be positive. In other words, only part of the stress power goes to changing the energy, and the rest is dissipated. So this is the typical scenario. And in this case, you have dE dt is minus d, where E is, or let's put it this way. Make the kinetic explicit. E is the strain energy minus the potential energy of the loads. Okay? So here then, if you have a positive definite dissipation, this will be negative definite. So you always have less than 0 or less than or equal to 0 in any realizable process in a typical case. So you can generate an inequality like this if you have thermoelasticity with heat conduction, which is a dissipative process, or if you have elasticity augmented by some dissipative or viscous stresses, for example. You can generate a structure like this. So if you have an initial condition, an initial configuration, right, which is not an equilibrium state, and if this tends asymptotically to some configuration, say t equals 0, let's have an initial velocity 0 there, although this is only, the acceleration is not 0 at this time, so we don't have an equilibrium state. We don't have a state of mechanical equilibrium. Then the kinetic energy plus potential energy at infinite time is less than or equal to, is bounded above by its value at the initial time. And if this is a state of mechanical equilibrium asymptotically stable, then the kinetic energy vanishes there. By construction, the kinetic energy vanishes here. So that the energy, the potential energy at the asymptotically stable state is bounded above by the initial potential energy. So that's essentially this statement. So we can use simply the fact that in any real process is dissipative to generate this again as a necessary condition for asymptotic stability. So for finite elasticity, conventional finite elasticity, this is the condition that people focus on. And there's a vast literature from the mid-1970s or so concerned entirely with this minimization problem. Find x such that E at x plus delta x is less than is greater than or equal to E at x for any kinematically possible delta x. So this is a pure variational problem of minimizing the energy. And there's a huge literature on it. For example, famous existence theorems for this problem by John Ball, who was subsequently knighted for his achievement in proving the existence of x such that this is true in the nonlinear conventional finite elasticity problem, is concerned only with establishing the existence of states that satisfy this. Even those states, after all the much beautiful analysis, we have, as of today, no rigorous proof that such states are actually stable in the Lyapunov sense. So there are many open questions in finite elasticity that persist even to this day. However, we can even if we satisfy this, we don't guarantee stability of our solution. Such a state will be in equilibrium by virtue of the fundamental lemma of the calculus of variations. That's easy to show. But even such equilibria are not guaranteed to be Lyapunov stable. Failure of this guarantees that they're Lyapunov unstable, however. So the current state of the art is centered on study of that problem. And even a complete characterization of this problem, which is beyond our reach currently, does not guarantee stability. So there are many open problems, and I think I can leave it there. And there are some notes available if you want to do some homework and do some extra reading, Coiter and so on. Okay? Thank you.